Okay, let's start this talk by coming back to our big picture. Remember, for this course, we are in quantitative world, and first we are discussing the descriptive statistics, because in real life, when we have a data set and we are going to present results to our readers, we always want to describe the data, describe what's going on with our data. And the first way we do that is through measures of central tendency, measures of spread outness or distribution or variability, and then finally measures of distributional shape. Okay, so that's kind of where we are. We've talked about these two. We've kind of thrown in a discussion of standard scores, and that you'll see that come up again today. And so with this talk, we'll move on to measures of distributional shape. Okay, so let me back up to the beginning, and let's take a look at these three pictures. Now, granted, these are not the best pictures, but they are just intended to make a point. So if you look at each of these distributions, and remember, distributions are our sets of scores. So in this case, we have three sets of scores. Maybe they're scores from three different classes. Maybe they're scores from three different grade levels, or even three different campuses, three different districts, whatever works for your context. Excuse me. So imagine that each of these distributions or sets of scores has a mean of 50. Also, each distribution has a standard deviation of 10. So the spread of the scores is 10 around the mean. Okay, so if we were only given the mean and standard deviation, we might assume that these scores look the same. And you can tell just from this very kind of roughly drawn example that the first distribution here, kind of think of this as the first, is a little bit different than the middle one here, which looks more like our nice bell curve. And also compared to this one over here, that this one is kind of skewed a different direction. This one looks like it's skewed a little bit to the right. This one seems to be kind of dead on, and this one is skewed a little bit to the left, right? So if we only knew mean and standard deviation, we really wouldn't have the most correct kind of picture, mental picture it might be, of the distribution. So we need more. We need something or some things that are going to help us with that distributional shape. All right, and we have two of those. We have skewness and kurtosis, and they're kind of like peanut butter and jelly. They go together, but let's look at skewness first. All right, so skewness helps describe our distribution beyond central tendency and variability, and that's kind of what we just talked about. If you think skewness, think symmetry. So skewness talks about how symmetrical your distribution is. So think back to probably elementary math at some point where you talked about symmetry. Do your two sides match? And in this case, we're going to fold our distribution on the mean and think about whether or not our two sides match. Okay, so skewness, symmetry. Luckily, they both start with an S, and that kind of helps a little bit with the keeping track of all of this. All right, so let's look at these examples here. Now you can tell I was working on this earlier, so I'm going to give this a little erasing. Take a look at these three pictures. When we think about symmetry, we really have a few options here, I guess you could say. So we could have a distribution that's positively skewed, negatively skewed, or not skewed in that it's perfectly symmetrical. Excuse me. So if it's not skewed, we say it's perfectly symmetrical. So you can imagine that if the mean is somewhere around 10, if we folded the distribution right on that mean, and that's not a very straight line, is it? The two sides would match. So we say it's not skewed. But what I don't like about this example is a lot of times when we see an example of skewness being near zero or at zero, which means it's not skewed, it has this nice bell-shaped curve. But what I want to point out to you is it's not always going to be that way. Because skewness is just talking about symmetry, you could have a situation, I'm going to see if I can draw it better this time. You can have a situation where you have something like this. Let's see how close I can get. All right, and let's assume our mean is somewhere right here. So if I were to take this distribution and fold it on the mean, you can see how our two sides would match. So just imagine these are drawn in an identical way. But the two sides would match. So this distribution right here, which is clearly not a nice, pretty bell shape like this one is also not skewed. Lovely handwriting. This one is not skewed. Okay, so just because it's a non-skewed distribution doesn't mean it's going to be this nice bell shape. Not always the case. Yeah, sometimes the case, sure, but not always. It could be more of a situation like this. Okay, if we have one of these other options, either positively skewed or negatively skewed, I want you to try to keep something in mind when you're thinking about which it is. So if it's positively skewed, try to remember that that word positive is really talking about the tail of the distribution. So if it's positively skewed, the tail is going to go toward the higher numbers or the larger numbers. Conversely, if it's negatively skewed, again, that word negative is talking about the tail. So the tail is going to go toward the lower numbers. And I don't want to confuse you by saying this, but to me, this idea here that positive talks about the tail and negative talks about the tail, that seems so counterintuitive to me. It seems completely backwards because in my mind, I want to consider where is the hump, right? So if the bulk of the scores or the hump is somewhere, I want to relate that, so if the hump is toward the lower numbers, I want to say, oh, that's negatively skewed, and then vice versa with the positive. But it's actually the complete opposite. The positive and the negative, they're actually talking about the tail. So when you're thinking about skewness and kurtosis, if you have that immediate kind of association like I do, just think, nope, it's backwards. It's backwards from what I think. And the reason is it's talking about the mean. So when it says it's positively skewed, it's actually talking about the mean is being pulled toward the tail. The average or the mean is being pulled out here. And the same thing down here. We might expect our mean to be at negative 30 because that's where the bulk of our scores are. But really, these kind of outlier-ish scores, they're pulling our mean this direction. You see what I mean? So the influence of these scores down here, even though there aren't many, it's enough kind of to send our mean out of the hump, in other words, and for lack of a better term, but out of the hump and toward this direction. So if it's negatively skewed, the tail goes toward the negative numbers. See what I mean? And the reverse is true here. You can think of this in, a situation like home prices, where they so often use the median because of issues like this, where you might have the majority of people, say this is an affluent neighborhood, and the majority of people are around $350,000 to $400,000 house, but yet you have some people with 6, 7, 8 million plus houses. And so what the average person in a wealthy neighborhood anyway, in this neighborhood, the average person might actually be around here, but the average is looking higher because the mean is being pulled toward the tail because of the influence of those very pricey homes. So that would be an example of being positively skewed because our value is being pulled toward the higher numbers. Here, the reverse is happening. Our mean value is being pulled toward the lower numbers. Okay? Let's go to the next slide. There is a formula for skewness, and in semesters past, I have asked students to calculate skewness, and we've gone through some examples. But really, I think looking at an example on SPSS is going to be more helpful and has been more helpful. But I do want to point out some things here to you. So we talked about z-scores, and those are your standard scores. So when we're looking at skewness, we standardize the scores, take it to the third power, sum it, and then divide by the number of scores. But the takeaway I want you to remember is what's going on with the numbers. So if you have a distribution that's perfectly symmetrical, your skewness will be around 0 or right at 0. If you have a positively skewed distribution, remember that's talking about the tail. If the tail's going toward the higher numbers, you'll have a skewness that's greater than 0. And then if it's negatively skewed, you'll have a value less than 0. So luckily these are kind of the way they have these done is kind of intuitive. So negatively skewed is going to have a negative value. Positively skewed will have a positive value. Okay? So far so good? In just a little bit we're going to pull up a small data set and kind of go through some practice looking at and kind of tweaking our skewness and kurtosis using SPSS. All right. So let's continue. Here's an example of 3 kind of small data sets, 3 distributions that all have a skewness value of 0. All right, so imagine here, this is our mean. The mean is marked with the little line on the x-axis or the number line. So if we folded this distribution in half on the mean, you can see that the 2 halves would match. So in this case is a skewness value. So if I did skew, equals 0. Same here, skew would also equal 0 if we folded it in half. And the same thing here, if we folded this distribution in half, it would also be symmetrical, right? But we can also see that even though they all have the same skewness value, they clearly are different. And so this kind of brings up the other piece of information we need. So skewness gives us some info about the shape of our distribution. It talks about symmetry, but we need kind of that height to width ratio information. Because clearly they can all have a skewness of 0, but they do not look the same. So we need the peanut butter with our jelly. We need the other half of our shape information. And that is kurtosis. So, and this says the distribution is bimodal, which it does have 2 modes, but it is still symmetrical. We need more to really describe this distribution, right? Okay, and so that is kurtosis. Kurtosis describes the height to width relationship in the distribution. And again, there is a formula for kurtosis. We'll look at that in just a second. But let's look at just kind of a few pictures that describe some options for our kurtosis. So just like skewness, if the kurtosis is normal, it's going to have a value of 0. And so you can see that this has a really nice height to width ratio. It's pretty nicely done. In the next example, we have a kurtosis that's positive. Now this isn't the best picture, we'll say. It should look visually a little bit taller and thinner, but anytime your distribution is tall and thin, you're going to have positive kurtosis, and we call this leptokurtic. So if your distribution is tall and thin, it's leptokurtic and positive. The reverse is true here. If you have a shorter and flatter distribution, distribution is short and wide, kurtosis will be negative or less than 0. All right, and I have kind of a silly way to remember this. Platykurtic, I think platy, fatty, it's short and fat. And then leptokurtic, the L is kind of tall and thin, so that makes me remember, oh, leptokurtic is tall and thin. All right, and so negative numbers, you're going to have a platykurtic distribution. Positive numbers, you're going to have a leptokurtic. And then if it's normal, just nice heights to width ratio, then kurtosis will be 0. All right, the formula for kurtosis is here. And like I said, we have gone through and calculated kurtosis. But in reflecting on those lessons, I really think it's more valuable to look at it kind of in a applied, hands-on type way. So we're going to hold that off. But again, we do have our z-scores, so our standard scores are showing up here, taken to the 4th power, summed, divided by n, and then subtracting 3 to get those kurtosis values. All right, so here are a few examples. Let's look at this. Let me get my pen to write again. Okay, so would the kurtosis be positive or negative? So I think the best would be to try to scratch it out over here. So if this is 1, 2, 3, 4, 5. All right, so I'm going to have one score, if it's going to let me do it. I'm going to have, that stinks, one score on each one. All right, so if you're thinking about, now you have to kind of imagine the line, the curve drawn in your head, like that. Would that kurtosis be positive or negative? Remember your little rhyme, flatty, platy. If it's platykurtic, it would be negative, right? Negative. All right, so let's do the next one. 1, 2, 3. Okay, so we have 1, 3, and 1, 1, and then how many 2's do we have? 1, 2, 3, 4 2's. 3. Oh, that's terrible. Okay, so again, I'm going to draw that curve over because for me, that's really helpful. So I'm going to force my learning style on you. All right, so leptokurtic, right? It's making a tall distribution, like the shape of that L. If it's leptokurtic, I know it's going to be positive. All right, so let's try this last one. Oh, it's just a 3, isn't it? How many 3's? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oop, that's terrible. 6. Okay, so you get the picture here. Positive or negative? Positive or negative? What do you think? I need some Jeopardy music to pipe in. All right. If you're a little stumped on this one, maybe you're not. Usually in class I get votes for positive and negative, and then I get lots of I'm not sure faces. So I'm just going to look at this formula again quickly. And what I want you to notice here is the z-score. Do you remember the formula for z-score? Remember how we had our score minus the mean divided by the standard deviation, right? Remember that? That's your formula for z-score, right? So I know that in order to calculate kurtosis, I've got to convert all of my scores to z-scores first. Okay, so do you see what's going to happen when I take that first step before I can even think about calculating kurtosis, right? So what is this down here? If I'm thinking about my example, I have all these 3's, right? 4, 5, 6. So what's my standard deviation here? I don't have one, do I? It's 0. There's no standard deviation. They don't vary at all. You know, if we imagined our picture from before, we had a kind of a column of scores, didn't we? So there's no variation. There's no standard deviation. So it's going to be 0, which is undetermined, right? We cannot calculate z-scores. So it's not really a trick question. I don't like to think of them as trick questions. These are our thinking questions. So this one, it's kind of NA, or cannot be determined, because we cannot follow through with our formula here. We can't do anything, can we? We're kind of stuck. So it's undetermined. And if you think about it, that makes sense, because if this is a height to width ratio and we have a column of scores, that we can't really describe it as a height to width ratio, can we? Okay, so let's continue. How does distributional shape relate to central tendency? Okay, so the mean, like I was talking about earlier with home prices, the mean is impacted by extreme scores. All right, and if you think about that, that makes sense. So say you're in a classroom, and maybe you're a student, and everybody scores around 70, except you have 3 or 4 people who score 98, 99, 100. They're going to mess up the mean, aren't they? They're going to pull that mean toward the higher numbers, toward the 80s and 90s, when in reality most people scored around 70. Okay, so the mean is impacted by the extreme scores. The mean is pulled toward the tail, which we talked about earlier, and away from the median. Again, that's why they use median a lot of times when they're talking about home prices, because the mean can be pulled toward the tail and away from kind of what's really happening, but the median is a little more stable in situations like that. In a non-skewed distribution, so if it's non-skewed, what is our skewness going to be? If it's non-skewed, it's going to be 0. If you have a non-skewed distribution, the mean, the median, and the mode are the same value. Okay, so just some facts to remember and think about. All right, and here's a little visual of it. But your mean is going to be pulled toward the tail, even if it's just a little bit. Oops, my pen went away. It's going to be pulled toward the tail and away from that median. And then the opposite is true here. It's going to be pulled toward that tail. Okay, so that concludes our discussion of measures of central tendency. We'll look at some here in a couple of minutes on SPSS, just to do a little bit of practice. So I will stop the recording.